Good morning, students. Very good morning to all. Today we have to discuss about thermochemistry. Thermochemistry. So, what is the thermochemistry? It is the physical chemistry. It can deals with the transfer of heat between system to surrounding, whether phase change or chemical reaction takes place within the system. So that is called thermochemistry. Okay, your syllabus we have to read thermochemical reactions. Thermochemical reactions. What are the thermochemical reactions? In balanced chemical reactions, heat energy transfer from system to surrounding. Heat energy transfer from system to surrounding. Reactants undergoing to completely reacted. Understand now? That is thermochemical reactions. Generally we have two types of thermochemical reactions: endothermic, exothermic. Here endothermic means enthalpy change equal to positive. Exothermic means enthalpy change equal to negative. Okay, we have to discuss one by one. Endothermic and exothermic. Right, first one, endothermic reactions. Endothermic reaction means the system absorbs the heat energy. That means a reactants absorb the heat energy. So reactants absorb the heat energy and undergoing to break down the bonds. Okay, so here endothermic means absorb the heat energy. Absorb the heat energy. Understand that? So chemical reactions means reactant. Reactants absorb the heat energy undergoing to break down the bonds. Okay, that is endothermic process. In endothermic process, enthalpy change equal to positive. Enthalpy change equal to positive. If you write down the graph between enthalpy change to state function, enthalpy change to state function, like that come. This is product, this is reactant. That means here enthalpy change equal to enthalpy of product minus enthalpy of reactant. That means products more than reactants. That's why enthalpy of product more than enthalpy of reactant. Enthalpy of product more than enthalpy of reactant. Next, another one. Here reactant stability more than product stability, because when the heat energy absorbed, more energy required to, in endothermic, more heat energy required to break down the bonds of reactant. Whenever in any chemical reaction, more heat energy required to break down the bonds of reactants makes less stable product formation. a reactant stability more than product stability. What is the reason means more heat energy required to break down the bonds of reactant. That's why reactant stability more than product stability. Okay, so here more heat energy required for break down the bonds of reactant. Break down the bonds of reactants. Okay, so here reactant stability more than product stability. Next point. Representation of endothermic process. Representation of endothermic process. Okay. Representation of endothermic process. For example, A plus B gives rise C product del H equal to plus X kilocalories. This is endothermic representation. While problems we should find out. Otherwise, A plus B, okay, A plus B plus X kilocalories gives rise C. This is also endothermic process representation. Next, otherwise A plus B gives rise C minus X kilocalories. This is also representation for endothermic. This is minus. Okay, so it is the representation for endothermic process. Next one, exothermic process. Exothermic process means heat energy released from the system. So here heat energy release. That means here heat energy release when the reactants converts to the product. That means here less heat energy required to break down the bonds of reactant. Okay, because heat energy released. Okay, if you observe graph, enthalpy change to state function. Okay, here like that. This is reactant, this is product. Okay, here reactant dominated product. In exothermic, reactant dominated product. So here del H equal to Hb minus Hr. Enthalpy of product minus enthalpy of reactant. Here enthalpy of reactant greater than enthalpy of product. That's why here del H equal to negative. That's why here del H equal to negative. Before endothermic reaction, enthalpy of product greater than enthalpy of reactant. That's why their del H equal to positive in endothermic. In exothermic, enthalpy of reactant greater than del H equal to negative. Next, another important point here, product stability more than reactant stability, because here heat energy released now. That's why less amount of heat energy required to break down the bonds of reactant. Less amount of heat energy required to break down the bonds of reactant. That's why here product stability more than reactant stability. Product stability more than reactant stability in exothermic process. Okay, then next one, representation of exothermic. Representations are very important amount. So while calculation sums very important. Representation of exothermic. Representation of exothermic. Okay. A plus B gives rise to del H equal to minus X kilocalories. This is representation for exothermic. Next, A plus B gives rise C plus X kilocalories. This is also representation for exothermic. Next one, A plus B minus X kilocalories gives rise to. This is also representation for exothermic reaction. So these are the representations of exothermic. So a main important one, listen amma, product stability directly proportional to heat energy release. Inversely proportional to heat energy observed. So that's why heat energy released means exothermic. Heat energy observed means endothermic. That's why product stability more in exothermic, less in endothermic. So here more heat energy release means more product stability. More heat energy absorbed means less product stability. Okay, so in any two reaction comparison, one reaction more heat energy release than another reaction means that reaction product formation also more, product stability more. That's why here more heat energy release, more product formation. More heat energy release, more product formation. More heat energy observed, less product reactions. Okay, these are the examples for endothermic process. Dissociation reaction, vaporization reactions, sublimation reactions, fission reactions, photosynthesis reactions. Next, examples for exothermic. Examples for exothermic. Respiration reactions. Respiration reactions. Next, combustion reactions. Burning reactions. Combustion reaction, burning reactions. So this is examples for exothermic. Next, formation reactions. Enthalpy formation reactions or heat formation reactions. Heat formation reactions. Okay, maybe endothermic and exothermic. Okay, both endo and exo. Some reactions endo, some reactions exo. That means formation reactions exist in some reactions in endo, some reactions in exo. Okay, this is so formation reactions exist in both endo and exo. Next one, heat formation. Heat formation. Before introduction part, we learning about before heat formation. Heat of the reactions. Heat of the reactions. Heat of the reactions or enthalpy of the reactions. Enthalpy of the reactions. Enthalpy of the reactions. Heat of the reactions. Okay. What are the heat of the reactions or enthalpy of the reaction means? The amount of heat evolved. Evolved means released. The amount of heat evolved. Evolved means released. The amount of heat evolved or observed. Observed means capturing. So the amount of heat evolved or observed when 1 mole of the reactant completely undergoing to reacted. Reacted means completely converts to the product. Okay, so heat of the reaction, enthalpy of the reaction means heat energy evolved means released or observed. Evolved or observed when 1 mole of the reactant. So it is explained in the version of reactant only. In terms of reactant only, heat of reaction explained. In terms of product cannot explain. In terms of reactant only explain. 1 mole of the reactant completely undergoing to reacted. Reacted means completely consumption. Completely reacted converts to the product. Okay, so amount of heat energy evolved or observed when 1 mole of the reactant completely undergoing to reacted. That is called heat of the reactions or enthalpy of the reactions. So this is may be endothermic or exothermic. So here we should following balancing. In balanced chemical reactions only, okay. So amount of heat energy released or observed in balanced chemical reaction, 1 mole of the reactant completely undergoing to reactant. So we should follow stoichiometry. Stoichiometry means balancing. Number of moles of reactant equal to number of moles of product should be required. Balance is required. Okay. So factors influence for heat of reaction. Factors influence for heat of the reaction. Heat of the reactions. Factors influence. First one, at constant temperature, whether pressure or volume constant also reaction takes place. So reaction takes place at constant temperature, whether volume or pressure at constant. Volume constant means heat energy. So the reaction takes place at constant temperature, whether volume or pressure at constant. So your heat energy transfer. Heat energy transferred at constant volume means del U. Heat energy transferred at constant pressure means del H. That's why del H equal to del U plus del nRT. Okay, so reactions carried out like that. Next, second one, quantity also. Heat of reaction depends on quantity. So second factor depends on quantity. Depends on quantity. For example, H2 plus half O2 H2O minus X kilocalories, for suppose. Next, 2H2 plus O2 2H2O. Now we write as a 2 into minus X kilocalories. That means if coefficient associated with reaction means same coefficient multiplied with heat energy also. If coefficient, 2 is the coefficient. If coefficient multiplied with reaction means same coefficient multiplied with the heat energy. Understand now? That is the second one. Next, third one. Allotropic nature. Heat energy depends on allotropic nature. Allotropic nature. For example, carbon graphite plus burned with oxygen, carbon dioxide. Here heat energy release, for suppose minus 393.5 kilojoules per mole. Okay. Next, C diamond plus O2 CO2. Here del H equal to minus 398.5 kilojoules per mole. Carbon same element but one allotropic form to another allotropic form, heat energy will be changed. Carbon in the form of graphite minus 393.5 kilojoules of mole heat energy released. In the form of diamond minus 398.5 kilojoules per mole of heat energy released. So allotropic form also will decide. Next one. Next one. Physical state. Physical state also influence amount. Physical state also influence the heat of the reaction. For example, H2 plus half O2 H2O liquid. Okay, here gas. Here del H equal to minus 283.5 kilojoules per mole. Next, H2 plus half O2 gas. Here H2O also vapor, gas only. H2O vapor form. Here del H equal to minus 242 kilojoules per mole. That means H2 plus half O2 formation water. If water formation in the state of liquid means 283 kilojoules of heat energy released. If water formation in the state of vapor means minus 242 kilojoules per mole of heat energy released. That means compared to vapor form formation, liquid form formation, more heat energy released, because compared to vapor, liquid energy required more heat energy released. Okay, that means here gas to vapor, almost vapor means gas. Here gas converts to gas. Here gas converts to liquid now. That's why when the gas converts to liquid means more heat energy released. Here same status, same phase. Here gas phase, here gas phase. Okay, here gas phase, here liquid phase. That's why when the gas phase converts to liquid phase, more heat energy release. These are the influence factors on the heat energy. Okay, next types of heat of the reaction we have to discuss. So generally your syllabus heat of reactions heat of the reactions. Okay, heat of the formation. This is also called enthalpy of the formation. Heat of the formation. Second one, heat of the combustion. This is also called enthalpy of the combustion. Next, heat of the atomization. Fourth one, heat of the neutralization. Next, heat of the hydration. Next, heat of the hydrogenation. Next, finally, bond dissociation energy. Bond dissociation energy. So in your syllabus, these concepts we have to read it. So your syllabus more important, heat of formation more important, heat of combustion more important, heat of the neutralization more important, bond dissociation energy more important. From these four concepts, sums come and theoretical questions also come in. Understand now? Then before these terms we have to read, you should know some elements standard state. of the reaction we have to take or we have to consider stable state of the elements only, or standard and stable state of the elements only we have to consider. That's why, so elements stable and standard state you should know it. Carbon, graphite. In graphite form, stable state. Carbon means graphite. Next, sulfur, rhombic state. Sulfur, rhombic. Phosphorus, white allotropic form. Hydrogen, nitrogen, oxygen, gas form. That means diatomic gas form. So that means H2, N2, O2, like that. Next, bromine, Br2. Okay, gas form. Gas form. Gas form, diatomic gas form. H2, N2, O2, Br2. Next, metals. Metals. Metals, solid form, solid state, except mercury. Except mercury. Mercury liquid form, except mercury. Mercury liquid form only stable. Metals, water, H2O liquid form. H2O liquid form. Carbon dioxide vapor form or gas form, that means vapor form. Minimum, you remember this part of your syllabus. Carbon means graphite state only stable. Graphite allotropic form only stable. Sulfur means rhombic only stable. Phosphorus means white phosphorus only standard and stable. Hydrogen, nitrogen, oxygen, bromine. So in the form of diatomic gas forms, diatomic gas forms, molecular forms, molecular forms. Okay, H2, N2, O2, Br2, molecular forms. Metals, solid state only stable except mercury. Water, liquid form. Carbon dioxide, vapor form. Okay, these standard states and stable state you should remember. Okay, next class we have to discuss one by one. All heat of the reactions we have to discuss.